here, you know, it's not anything, but when you get up close to it, then it goes off. So, why is that? In order to talk about radioactive minerals, you have to get a little bit into particle physics. Of course, I'm not going to get like I don't even know particle physics, so I'll have to get way into it. But, you know, just the basic, you know, 30,000 foot view kind of thing. And there's two basic things that you kind of need to know. One are the four fundamental forces of physics, of nature. And the other is kind of the general idea of how an atom works, you know, like where the nucleus is, the electrons, what the nucleus is made of, that kind of stuff. That's basically about as deep as we're going to go into any of this. So, the four fundamental forces of the universe are the strong nuclear force, the weak nuclear force, I know that's really easy, gravity, and electromagnetic radiation. We're going to abbreviate it like that. So, these are basically the four forces that govern everything that is, you know, inherent with classical mechanics, with quantum mechanics. Oh, actually, quantum mechanics it gets kind of fuzzy, which is why we can only do a 30,000 foot view, because quantum mechanics and classical mechanics are two animals that aren't even close to the same species. Basically, of these four forces, does anybody know what the strongest one would be?
Depends on how far away you are.
No. Just the fundamental force of gravity is a force per unit mass, but
right.
Yes.
Well, the strong nuclear force is the strongest, but you
got
have
it.
to be
Yep.
in a nucleus to feel it.
That's exactly right.
So it depends on where you are.
It only stretches like 1 to 2 femtometers, which is like the next step down 1,000 below a picometer. Very, very small. And the weakest is gravity. So, I mean, you know, everything in here is held down by gravity, but, you know, I can take this piece of metal here and take a magnet and pick it up very easily. I can overcome gravity with magnetism, with just about anything. So gravity is actually very, very weak. In fact, it's 0.37 zeros and then a 1 weaker than the strong nuclear force. So it is literally orders of magnitude stronger, the strong nuclear force. And if you think about it, it kind of makes a little bit of sense. The nuclear bomb was, that energy that was released was from the strong nuclear force being basically broken, which releases a ton of energy. And actually, the nuclear bomb that was dropped on Hiroshima only had a yield of like less than 1%. So literally less than 1% of the material that could have split. So it could have been just that much bigger. And of course, Nagasaki was bigger. Then we got to the hydrogen fusion bombs, which are even bigger, and just, you know, go crazy amounts of energy when you get to the strong nuclear force. The weak nuclear force we'll cover here a little bit in just a minute, because it kind of tells dictates one of the particles that are released when we're talking about radioactive minerals. So when we're talking about radioactive minerals, sorry, I forgot I have a periodic chart here to point at as well, courtesy of Julie's printer at work, because she can print out in larger amounts than I can. So the minerals that are sitting there are, one is called gumite, which is actually literally named because it looks like gum, like tree resin gum. And the other one is autunite, both of which are uranium ores. And of course, uranium sits down here in the actinides portion of the chart. Now, the reason that uranium is radioactive, and basically every element that's past lead on the periodic chart is radioactive, is because, so here's an atom, this is the nucleus of an atom, and it has other shells where the electrons basically float around. The protons and the neutrons all sit in here. So you've got in uranium, was it 92? Yeah, 92 protons. And the number of protons that an atom has dictates what the atom is. So 92 protons is always uranium. It can have more or less neutrons in it, and the number of neutrons plus the number of protons gives you the atomic mass. So That's what isotopes are basically like uranium, 92 protons, but it might have 143 neutrons for uranium, whatever that added together would be, or 142 neutrons, or 141 neutrons. So those are the different isotopes of an atom. So the main isotope that's in those minerals is uranium-238. That's generally the uranium that is found in most minerals. It's about 0.7% uranium-235, which is the really nasty uranium that when they say enriched uranium, that's getting the uranium-235 out. So about 0.7% is what's left now because it has a half-life, and of course, as the Earth has aged, half of the uranium-235 goes away in a certain amount of time, and yada yada. So we're down to about 0.7% is the uranium-235 content in pretty much all uranium minerals. So the nucleus, when it gets above 82 protons, which is where lead sits, is 82 protons, it's basically like Dave was talking earlier about the strong nuclear force. What the strong nuclear force is, hello.
Hi.
So what the strong nuclear force is basically the glue that makes these things stick together. These protons and neutrons here stick together. So the protons are all positive, so they don't like each other. Electromagnetic force would say it wants to push itself apart. But the strong nuclear force keeps it together, basically the glue. But like Dave said, it only is effective to about 1 to 2 femtometers, which is 1 times 10 to the negative 15th meters. So very, very small area. The radius, or the diameter of a uranium nucleus, while it's not actually like a circle, it kind of undulates like a drop of liquid kind of, but is generally approximately 15 femtometers. So the electromagnetic force is trying to push it apart. The strong nuclear force is trying to keep it together. But since the uranium atom and all the other atoms above 82 protons on the periodic chart, they have too many to be able to stick together. Basically, the protons on this side can't talk to the protons on that side. So the electromagnetic force basically overcomes the strong nuclear force, and it spits out what is called an alpha particle, is where the decay chain of uranium is actually like 14 steps. And basically there are 3 different types of radiation that will come off of any radioactive specimen, or at least 3 primarily. They are alpha particles, beta particles, and gamma rays. So alpha particles and beta particles are actually particles. They have mass. They are a thing. An alpha particle is actually 2 protons and 2 neutrons, which is essentially the nucleus of a helium atom. So when this thing decides, okay, I've got too many neutrons in here and I can't stay together like this, it spits out 2 protons and 2 neutrons, so basically a helium atom. And it spits it out at like 5% the speed of light. I mean, just insanely fast. Then there is, so that's alpha decay. Then there is beta decay, which gets a little bit hairy. The weak nuclear force that we talked about earlier is energy that's basically stored within neutrons, which are neutral in charge, not positive or negative, that allow them to change from a neutron to a proton and spit out an electron in the process, and an antineutrino in the process. But those are another topic that we don't have time for today. So that's the alpha particles and the beta particles that get spit out, and then there are gamma rays that get spit out, which are basically just pure energy. So if you look at the electromagnetic spectrum, it goes all the way from one side, which is radio waves that has a very large wavelength. So you're looking at an energy wave here. This would be radio waves, and as you get closer and closer together, you get higher and higher in energy, and you go up the electromagnetic spectrum. So you start off at radio waves, and you go to microwaves, then you go to infrared, which is infra is before, so before red on the spectrum. Then infrared, then you go to the visible spectrum, which goes red, orange, yellow, green, blue, indigo, violet. And then once you get to violet, everything after that is ultraviolet, or the next one after that is ultraviolet, which means beyond violet. Then it goes to X-rays, and then the most energetic rays of them all are gamma rays. And gamma rays are let off when one of the two, or when the beta decay happens. It leaves the atom in kind of like a hyper energetic state. It gives off some energy, but not enough, and so the atom will literally be just sitting there vibrating, and it gives off a gamma ray, which is basically a photon of light, essentially, but super, super energetic. So very, very bad for you. Those are the kind of rays that when people are dealing with enriched uranium and they are exposed to it for 10 seconds at a short distance, it's gamma rays that basically flood their body and kill them very, very quickly. So let me make sure I'm not missing anything as I go along here. So that is the decay process of uranium. Like I said, it's about a 14-step process where it will essentially, on this periodic chart, start at uranium. It'll shoot an alpha particle, which drops it down 2 protons and 2 neutrons, so it's now thorium. Then it'll go through beta decay, which changes a neutron into a proton, so it goes back up 1 and becomes protactinium. Then it goes through beta decay again and becomes a different isotope of uranium. Then it goes through a couple of alpha decays to go to thorium, and then you skip over to radium, then beta decay, alpha decay. And basically it just goes back and forth, changing protons to neutrons and then spitting out protons, or sorry, the other way around, neutrons to protons and then spitting out protons, until it gets to a stable atom, one that it's no longer radioactive, it can actually hold itself together, which in this decay chain is lead. And it's actually lead in a lot of decay chains. There are a few others that start out higher that end in bismuth. Even though bismuth is radioactive, I think one of the isotopes isn't considered. And then there's other radioactive minerals like carbon-14 that obviously stop at carbon, or yeah, carbon or boron. Stop somewhere else, it's not lead. But anyhow, so that's how radioactive decay happens. And when you actually are hit with radioactivity, essentially, you get the gamma rays, the alpha particles, and the beta particles. Now, alpha particles are, comparatively speaking, very, very big. They're very heavy compared to electrons and compared to the zero mass of a gamma ray. But they're so heavy that basically they can't pass through material as easily. So you can block alpha particles with a sheet of paper, or your skin. Your skin blocks alpha particles, so it doesn't really hurt you any. Beta particles are basically high-speed electrons. So they're electrons that were spit out during the beta decay, and they get spit out at about 90% the speed of light. Gamma rays get spit out at 100% the speed of light, which, kind of fun fact, the ones that are leaving this rock right now, if they're aimed at the moon properly, they will actually reach the moon in about 1.3 seconds. That's how fast the alpha particles are, the gamma rays come off of those. The beta particles, if they didn't get stopped along the way, they don't travel that far, but if they didn't get stopped along the way, it'd be like 1.5 seconds that they would get there. That's how fast everything gets shot out. And then, like I say, the alpha particles, about 5% the speed of light. So much, much slower, much heavier, so easily stopped by light paper. The beta particles, usually you need something like maybe a centimeter of aluminum or something like that would stop it. The gamma rays, nothing I'm gonna do is gonna stop the gamma rays. You need usually like at least several inches of lead, if not several feet of lead, or many, many feet of concrete. So thankfully, time, distance, and shielding is what they say are the 3 things that you need to concentrate on when you're dealing with radioactivity. Time, not being exposed to it for too long. Distance, like I showed you before, being 5 feet away from this, you basically have no extra radiation hitting you. And shielding, which is why I made this little lead box that's all lined with lead on the inside, just so I can carry it around and block at least some of what is coming out. So anyhow, I'm talking about all this random stuff, and I'm sure it probably sounds like Greek to a lot of people, just because autumnite's awesome. This is when they have a uranyl ion in the uranium ore, they fluoresce. Other ones that don't have a uranyl ion don't fluoresce, but the classic green fluorescing is caused by that ion, and it's just a beautiful color. But so yeah, I'm talking about all this stuff as though you actually have seen any of this. I was gonna try and keep this kind of like a secret, a surprise as to what I was building, and then I remembered that I am the worst person in the world at keeping secrets, and I think I probably told everybody what this thing is by now. So for those of you who don't know, this is what is known as a cloud chamber. When I talked earlier about why I decided to do this presentation on radioactivity, it really was because, as most of you probably know, I used to be a chemical engineer before this accident, and I still have an engineering mind, and I was the kid who used to take apart all of his toys, and sometimes put them back together, sometimes not, sometimes just leave them scattered all over the floor in pieces. But I just loved engineering and how things worked and pulling things apart and stuff like that. So when I found out that I had radioactive specimens, I was like, I've got to build a cloud chamber. But most of the time when people build cloud chambers, they do so by, they do so by basically what you have to do is get an enclosed chamber that has a supercooled floor. And when I say supercooled, I mean minus 26, I think is the cutoff. It has to be below minus 26 degrees Celsius. And so most of the time, the way that people do it is by getting a metal floor and putting dry ice below it. Dry ice is at like minus 75 or 76 degrees, so plenty cold enough to cool it down so that you can, and what happens is you basically create a supersaturated vapor layer very close to the plate. And what a supersaturated vapor layer does in this instance is all of the particles that I was talking about flying off there, close this so I'm not blocking half the people from being able to see me. All of the particles that come off of a uranium decay radioactive sample are considered ionizing radiation. And what that means is they have either enough power or enough power and a charge, a positive charge, to be able to literally rip electrons off of atoms as they pass by. So like as these alpha and beta and gamma particles, well the gamma particles not so much because they're so incredibly small, they don't hit the electrons often enough. But the alpha and beta particles will actually be traveling fast enough and with enough energy that the air molecules that are in there will have electrons ripped off of them, creating ions. And the ions create a seed point for the alcohol vapor to actually condense. So what it allows you to do is actually see the alpha and beta particles shooting off the specimen, and it leaves basically a contrail, like you'd see an airplane contrail. And you actually get to witness the radioactive decay. So I didn't fire this up while I was talking because it is an air conditioner. So it sounds like an air conditioner, and I didn't want to have to fight how an air conditioner sounds, but I can explain all of this to you as I go. So I didn't want to build one that required me to replace dry ice every 30 minutes, because that's just no fun. So I decided that I would try to make a unit that I could just plug in and get the cooling. And I didn't look how to do it before. I'm sure that someone else in this world has done this before me, but I never looked up to see if that was the case. And so it was a whole lot of trial and error. That would have been so much easier if I just like read an instruction manual on how to do it. So it took like 6 months to build. I don't know, what do you think, about 6 months? Thank God Julie is as tolerant as she is of my antics, because our living room has been this stuff, which gets on everything, and various electric components and stuff like that all over our living room for the past 6 months. So, but I think it's worth it. Hopefully Julie thinks it's worth it. I think it's worth it. So what I ended up doing is taking an air conditioner, which, as you can tell by the bottom, like 2/3 of this, it started out life as a normal run-of-the-mill air conditioner, probably thinking it was gonna keep everybody nice and cool in the summer, and I went and tore its head off.
Sorry to interrupt, I have a question.
Yes.
And I'm sorry because I was late, so I'm.
Yeah, no problem. Yes.
So this sample that we're looking at right now is giving off alpha and beta decay?
Yes,
Right now.
particles, yes,
Okay,
it's shooting
it's
off.
also giving off gamma radiation?
Yes.
This way? Okay,
Yes.
I need to be further back.
Well,
Is my
it's-
question.
The time distance shielding aspect of the radiation that comes off of here, the amount and the type is such that if you're more than about 3 to 5 feet away from it, you're getting the same amount of radiation that you get just from solar radiation that's coming. Yeah, you may not have seen it when you first came in here. I have a Geiger counter here that actually will tell you in microsieverts per hour, which microsieverts, there's two different ways, at least two different easy ways to measure radiation. One is CPM, which is clicks per minute. It's literally the number of times that this thing sees a radiation of alpha particle, beta particle, gamma ray, whatever. And that's the click that you hear, that click, click. And then it also can measure in microsieverts per hour, which microsieverts is a unit that basically they made up that is the impact radiation has on the human body. So basically at 100,000 microsieverts, you experience the very first ability to see any statistically significant change in your rate of cancer. So like 100,000 microsieverts is the cutoff bottom, and then up to, I think it's like 1 sievert or something like that, is basically you're dead within 3 minutes, kind of thing. So this thing, I actually calculated it out. To be able to get to 100,000 microsieverts, you would literally have to wear it as a pendant against your chest for about a year. And so, yeah, and as you see, when I get right up next to it, it really goes off. It takes it a second to cool down. But over here, it's nothing. It's basically like the radiation that you get, and if I turn this on with no mineral in the room, you would hear a click every couple seconds because of background radiation. Yes, sir?
That rock has radiation in it?
Yep. Well, it has.
And that's why it fluoresces?
No, it did fluoresce because it has the uranol ion, but it doesn't have anything to do with radiation. So the first person who discovered radiation, I can actually do this while I'm stirring this up. The first person who discovered radiation, or radioactivity, was a guy named Henri Becquerel. And he's a French person, a French scientist, who was very interested in phosphorescence. And some uranium salts phosphoresce. And so he thought that what was happening was the sun was hitting these uranium salts, and it was actually phosphorescing, not visible light, but phosphorescing X-rays, which X-rays had just been discovered like the year before, so they were like the new fad. Everybody was, ooh, X-rays, aren't they? So he basically took some photographic plates, wrapped them up in black paper so he could take them outside in the sun and it wouldn't expose them to light, and then put some uranium salt on it and left it there for a little while, and then came back and developed the plates, and sure enough, there was the image of the uranium salts, which he thought was the sun causing the mineral to give off X-rays, which caused the image on the plate. But France being France, it's not always sunny in France, or Philadelphia apparently. And so he had his plates and his uranium salts, plates all wrapped up in their black paper and uranium salts, and he stuck them in his desk drawer for like 2 weeks while the sun was not out. And for some reason that nobody knows why, he decided to develop those plates just for the heck of it, even though he hadn't brought them out in the sun and run his experiments on them. And when he developed them, he saw a perfect image of uranium, or the uranium salts. So he knew that it wasn't the sun that was actually causing the excitation of the elements and giving off these X-rays. He knew it was something that was within the actual atom that was giving off this energy by itself. He actually called them Becquerel rays. Thankfully, Marie Curie, like the next year, renamed it radioactivity, and so we don't have to talk about Becquerel rays, because who would remember that, except me. Yeah, this is basically constantly giving off alpha and beta particles. The alpha particles are probably going about that far, the beta particles are probably going about that far, and by the time you get out here, the gamma rays that are shooting out are missing you, mostly. So it's not really dangerous to be around this one unless you're just like on top of it for a long time. But as long as you're not doing that, you're okay. So we are going to, I like to use this one because it is the more active of the two pieces here. And what we do, get this silver stuff all over my fingers again. Wonderful. We take isopropyl alcohol. This is 99% isopropyl alcohol because you don't really want any water in there, like in 70% isopropyl alcohol, because it would freeze. I actually have a whole bunch of them right here.
Oh, okay.
I come prepared.
Good enough.
Yes, I come prepared. And rags. Let's see here. So, I'm going to take that isopropyl and one of these pipettes here. Put her on in the right direction. Ooh, and in the right spot. It's been a long time since I've been in chemistry lab. Long time.
What was the stuff you smeared on the top of it?
That is, yeah, sorry, I was meaning to keep telling you all that, and I stopped. That is actually a thermal paste. So what I did was I took this air conditioner and I ripped the head of it off, and I took the heat exchanger of the air conditioner and turned it 90 degrees so that it was horizontal. So that, when it's running, will get down to about -20, -24, something like that, which is just not quite cold enough for this. So then what I did was I took these things, there's 10 of them down here. I don't know if anybody, well, probably not, 'cause I had the paper over it. They're called Peltier coolers. So what they are basically little porcelain squares, like 1x1 squares that have two wires, one black and one red, coming out. And when you put electricity to them, it actually makes one of the sides cold and one of the sides hot. It's what they call a solid state heat pump. It basically just transfers the heat from one side to the other. And if you cool down the hot side really cold, like to -24 degrees, then the cold side gets even colder. So I can get my Peltier coolers down to roughly -45 to -50, somewhere in that range, which is plenty cold enough for this experiment to work. And to be in the habit of good handling procedures for this, I'll put on the glove. So, this is gumite. Gumite is kind of a slush fund of uranium ores. It's a whole bunch of different uranium ores that they just all label together as gumite. This one in particular has curite, which is named after Marie Curie, and uranophane. So that's the orange and the yellow. So these are what are known as secondary uranium minerals. Primary uranium minerals are things like pitchblende, stuff like that. They are usually very dull and kind of black or gray, not very pretty. But when they're exposed to air and moisture, they oxidize and become secondary uranium minerals. This on right. And they actually are more yellows and oranges and reds and pretty colors that collectors like. So this particular specimen here is an older secondary mineral. Uranium and all radioactive minerals go through a process called, I'm never going to say it right. Help me, Dave. Mysomictization, something like that. I'll look it up here in a little bit. It basically is the process of when the metamictization, that might be it. Yeah, metamictization, that's it, yes. Because the meta, of course, means it's transforming. So what metamictization is when uranium ores send off their alpha and beta particles, it's basically like a gun shooting a particle. You know, I mean, this alpha particle is being shot out one way based on the laws of thermodynamics. Every action has an equal opposite reaction. Just like a gun kicks back on you, these particles kick back on the minerals and literally will destroy the crystalline structure from the inside out. And so things like autunite is a relatively new secondary mineral, and it still has its crystallization and its crystalline form. It's very micaceous, like mica, in forms of sheets. But these minerals are much older and over hundreds of millions of years, or however long it took actually, it actually was shooting out particles. The particles would hit crystals and mess them up, and the recoil from shooting them out actually messes it up. And so you get this basically amorphous mass of mineral. Oh, I should have brought my fan. That's okay, this thing will be throwing out a bunch of air here in just a second, and I can use it like a fan. So what we're doing is I have a 1 Peltier cooler up near the top that is basically put into some felt. And I put the alcohol on the felt. And when I turn on this 1 Peltier cooler at a very low voltage, excuse me, it will heat up on one side, which helps vaporize the alcohol and also gives you a temperature gradient of warm on top and cold on bottom, which is what you need for the supersaturated layer to form. So it would help if I actually plugged this in. So that's this plug-in. This is for my lights that I made a custom light for, because in order for you to be able to see this, actually I should probably start this so it can start cooling down. In order to be able to see it, you really need light to be at like the level of where the supersaturated layer is and horizontal across. So I had to build a special light fixture basically to do that. Which, there we go. So now I just need to wait for about 2 or 3 minutes. So this is cooling, the air conditioner is running right now, and of course it is cooling down the heat exchanger, which in a normal air conditioner would then have a fan blow air across it. It cools down the air and it goes out in your house, it cools down the house. I took that fan out and instead put a copper plate on top of the heat exchanger. Copper is a very good conductor of heat, and so it conducts the heat away from the bottom of the chamber and down into the air conditioner to be able to be blown out by this this fan here, which is, there's actually 2 fans on them. One is to you blow heat across the heat exchanger when there's the hot, when you compress the fluid, the coolant in there, it heats up. You put it through a heat exchanger, blow a fan across it to cool it down a little bit, and then when you decompress it, it gets really cold, and you have another heat exchanger that you blow air across, and that's the one that blows out air into the room usually. I only have the one that, would be the one that you would normally hook the hose onto and stick it out your window because it blows the warm air out. But since I have very little warm that I actually need to take out of it, comparatively, I don't really need to exhaust it, so it doesn't heat up the room because there's not very much heat that it's pulling out of there. So, where's my I have my little temperature gun here that I just keep an eye on this. We're at about -6 Celsius. So when that gets to about -20, which will be in about another 60 seconds probably, then I can switch on the Peltier coolers. When I switch on the Peltier coolers, it gets really cold, down to like -45, -50. That creates a supersaturated vapor layer. Now the mineral is sitting in there right now, shooting out its particles as we speak, and it is ionizing the snot out of the air that's inside there. And when you get a whole bunch of ions that are all clogged up in the bottom of that thing, it makes it to where you can't see the particles anymore because it's already ionized everything and the vapor's already condensed, and so it makes it just a fog. So I had to put a high voltage, they call it a clearing field basically. It's a high voltage wire that's right up in the top here, and it's grounded at this plate here, and when I switch that on, it pulls all of those ions out and allows the new ions to be there and for the vapor to start, or for the condensation trails to start showing up again. So it's really kind of cool because if you look in there, like when I turn the Peltier coolers on, you won't be able to see the tracks yet until I hit the button to clear the field, and it's really kind of neat because they just kind of appear out of nowhere. It's like they magically appear. So if you want to come down here and be the first person, you can see the magic happen if you'd like. And then of course everybody else will be able to see everything also, but they won't be able to see it go from nothing to something. So you can hear just another, we're getting pretty close here. Yeah, good, another few seconds. We're about -15. So in just a minute, what you'll do is you'll just look right down in here, and you'll see things that'll appear between the mineral and the lights all around. There'll be a whole bunch of white streaks that should start shooting out everywhere. So
That's pretty cool.
it is pretty cool, actually. I know, I love it. Let's see. It is cooling down. And we're at minus 16, minus 17. Minus 21. Okay, I think we're getting close enough here. So now, yep, you should be able to look down in there and let me know if the magic. Oh wait, hold on. I got to hook up one more thing. Sorry, and I got to drop that too. That's all right. It's no worries. Yeah, the battery pack pops off. Sorry, I'm not too smart. Sometimes you got to give me just 1 second. Thankfully, since I have all of my stuff with me at all times, I can make up for my bonehead mistakes that I inevitably make, like putting a male connector where a female connector needs to be. That's okay. I'm with it. I promise. Give me just a sec. Just do that. That. Sweating like crazy. Knew I should have brought my fan. Okay, now we're good. You want to see it? Okay. All right, well, if anybody else wants to see it, they're more than welcome to. I'm just about to hit it. All right, you ready? 3, 2, 1. They appear. Oh, yep, there they are. Okay, yeah, you might need to get a little bit closer to be able to see, and it really, the radiation won't hurt you at all, like not a bit.
Oh, I can see
Yeah, you see the
it.
little streaks shooting out everywhere? Those
Yeah.
are
Like
literally,
snowball effect.
they're literally the alpha and beta particles that are shooting through the cloud of alcohol and ionizing the air and allowing the alcohol to condense on the actual ionized trail.
I don't see any streaks.
Between the rock and the light, you might have to get a little bit closer, like, so like, look right over here between the rock and the light. See the white streaks?
No, but that's, I don't know, does anybody?
Yeah, let me see if maybe. Oh, actually, you're right. They are not. Oh, yeah, they are, just very lightly. Light's light. Actually. Okay, now look. See the white streaks between the rock and the light?
Oh, a little bit, yeah.
Yeah, the lighting in here is a bit much. Maybe if we, yeah,
A little
can you turn
bit,
off the
yeah.
light? Yeah.
The light,
See if that might help it a little bit. Yeah, I can definitely see them. They're not as prominent as they usually are. I think the humidity is actually causing some problem in the air, but they are definitely visible if anybody would like to come see them. See it in action. Yeah, you know what it looked like before, and you can see now. See how they're a little bit lighter? I think the humidity is causing a problem.
Oh, yeah.
Do you see them down there?
Yes. It takes a second to like
Yeah,
focus on
yeah,
it.
you have to like focus your eyes in the right area. You have to look basically at the bottom plate almost.
I think I see what you're talking about.
Yeah, the white streaks between the rock and the plate there. Yeah, unfortunately, like I say, I think the humidity from all this rain is causing it to cloud up a little bit. Yeah. I think it'll look even better at the shop when it's not raining so much. Yeah, basically, this thing, I calculated it out. It was, if you actually, again, like wore it as a necklace for like 3 or 4 weeks, it was the equivalent of a modern day chest x-ray. So it's actually a very minimal amount of radiation, and about 90% of it is alpha and beta particles, and those are blocked by like your skin, so they don't really do any major damage to you. Yeah, you're probably better off looking at it this way. Yeah, that way I know was definitely better when I was doing it at home. You see the white streaks?
Yeah.
All right.
What's that?
Will it show up on photo?
Yeah, or show up on a video. I don't know if it'll show up on a photo if I catch it right, but a video for sure, because I took a video of it.
Is that posted on the Mineralogie Instagram?
Not yet. but
Not
it
yet.
will be.
Okay. All right.
Yeah,
All right.
I will post a video of it. You see him?
I do not think I see them.
Let's see. I wonder if I made
There's a
it.
little bit of cloudiness on the cover glass. And so just,
Oh, and actually, you know what? I could probably turn this down too a little bit. That probably would help. Oh, shoot. Wrong button. Oh, they're not showing up now.
I have that effect on all kinds of
Yeah, that's all right.
processes.
I do
Run out of
too.
alcohol?
Let's see. Oh yeah, it might actually be. No, it's still cold.
You guys pass that one? You need to pass that one?
Charlie, do you need the lights?
What's that?
Do you need the lights back on?
Yeah, you can go ahead and turn them on. I mean, there's no reason for them to be off. I don't think it made a big difference, but.
Okay.
Oh. Yeah, see, it's at like 1 degree. No, that's not right. This is still has frost on it. Well, all that buildup, and now it's not working right. Oh, for a second. Let's move that down. Plug everything in. That's plugged in. That's plugged in.
What is that black box in there right there? The fan stopping it.
This is just the lights.
Oh,
Yeah, it's a very, very low power, so yeah, the fan I don't think runs constant in that, it's just when it needs to cool down, and it's running at a very, very low power, so it doesn't need to cool down very often.
The light beam.
Yeah, and I love these two touch.
Mm.
There we go. It's almost like this thing is not clearing anymore. I don't know why that should be. Well, you know what? I am gonna put a new plate on there. Like I said, I was
substrate plate.
Well, no, this is a copper plate.
Okay.
It's copper that,
Oh, I thought this.
That's also
square
a
one
copper
was the
plate.
only one.
No. The actual base of this is a copper plate. That
Underneath the,
this is also a copper plate. It's
Okay.
just been oxidized or with liver of sulfur to give it a black patina, so that you could see the streaks more.
yes, that makes sense.
Yeah, it gives it a better. See, is that? Yeah, that's very cold. So it might be that I have a bad plate. So while everybody's just sitting here anyway, I'll change out this plate and see if it helps.
Well, while you're doing that, I'll mention that on Saturday, we have a field trip to the Starkville, Mississippi area. And there we encounter the Upper Cretaceous Prairie Bluff Formation, which hosts nice pyrite nodules of various sizes. And they go all the way down to little individual pyrite octahedra, which is hard to find in most places. And then there's also various mollusk fossils. So Upper Cretaceous, they're a little over 65 million years old. The very top of the Cretaceous is missing. It's about a 300-mile trip each way. So it's a long day. We're starting half an hour earlier than usual at 7 in the morning from the Lakeside Shopping Center, or 8 o'clock from the Mississippi Welcome Station on I-59. I'm sorry?
Isn't, Saturday election day?
Well,
Primary?
I've already voted.
Well, I meant, whether you have it or not, is it primary day?
It is primary.
Okay.
Doesn't change it. Doesn't change it.
I can only do what I can do, and I have guests the following weekend. And then I'm gonna be leaving to go to
4 hours.
Colorado for a while. I beg your
4
pardon?
hours.
Yeah, Sharon did it for, yeah, 4.5. And then there are several
Yeah,
spots
I
to stop
get
in
some
that
upset.
area that
I would love to
have
go.
written presentations.
What's that?
I would love to go on the strip, and I just got project
My contention is that
going.
Sure.
many of the
Yeah,
nodules have flown
Yeah.
from the remains of the soft parts of the mollusks. And they provided the iron that is half of the constituent of pyrite. You have 1 iron and 1 sulfur and each
Yeah, there we go.
of the iron sulfide compounds is pyrite.
Yeah. Okay. I had a bad plate. Anybody wants to see it now? It actually is working. Natural.
It's like
Yeah.
little jets.
Yeah, you see all the little. There's a whole bunch of streaks shooting out now. I don't know what I did wrong with that first plate. It's very odd.
Well, it could easily be the contact on the surface of the plate.
Yeah, it probably actually is the contact of the connector. It'd be my guess. But yeah, it just for some reason wasn't making good contact, so it wasn't clearing the particles.
That's cool. Oh man.
See them in there now?
I saw him better on her picture.
Oh.
Oh, yeah, now I see him.
Yeah, you have to like look at that plate at the bottom basically, because they're
Yeah,
not shooting
yeah,
out
no, I
all
see, yeah.
around. Yeah,
Yeah, that's.
yeah, they should be much clearer now. Yeah, yeah.
Right now, right? Like, no problem.
See them down there at the bottom?
They're cool.
Yeah.
Yeah, those white streaks.
I can't stand
When
it.
he was still like
Yeah.
trial and error, he's like,
And you can see like the alpha particles, they're the ones that make the really thick white trails compared to the other ones, and they don't travel more than like a couple centimeters at most. Their molecule is just such a big particle that it runs into everything else and
And then
stops
you'll
very
see them
quickly.
like a peripheral or around or straight through your vision, but you
Wouldn't
get
they
one
also be
specific
curved?
spot instead of like all
What's
that.
that?
That's the catch to that one.
Curved?
The trail?
No, they're
The
straight.
alpha
Video right now?
The beta particles then
Yeah,
go
yeah.
like
Yeah.
that as they bounce off of things, but the alpha particles are so big that they basically just bowling ball their way through.
That's right, it's like the fact that I stepped in an ant pile right
No.
after the second
No.
hit, so paranormal.
No, it's just literally
Here now.
yeah, it's literally just the temperature differential to cause the supersaturated vapor layer because you need something to be able to condense on that ionized trail to be able to see it.
I'm not really seeing much right now.
You're not?
Oh, see, I approached. the
That's
guy.
right, you keep
Dave,
close then.
stay away.
Yeah, of course.
Is this the online?
You see him in there? What's that?
This is the online.
That's the on night, yes.
Is it still there?
Let's see. No, they are there. I'm just gonna clear the field again. There we go. Okay, go for it. Oh, you know what it oh, I know what I'm doing. My clearing field runs on a battery, but the battery is almost dead. And I hadn't plugged it in. Why on earth was I not thinking?
I was gonna ask you that, Charlie, but I wasn't sure.
Oh, yeah,
Okay. Now try it. Let's see.
Break it, Dave.
There we go, sure. You see him there? Yeah, this thing is just not charged. I'm gonna let it charge for a little bit. It's not getting the full voltage, so it's not clearing the field properly. Okay. Plug in.
It's just a little more battery. It looks it. Okay.
Yeah, I need to let it charge for just a minute. The light is even going dim on it, so let me let it charge for 60 seconds or something. It's what it is a you know those tennis rackets that you hit mosquitoes with and it zaps them. So it's a high voltage, low amperage field. It puts out like 3,000 volts at like 1 milliamp. And so I basically just ripped that off and put a copper wire at the top and then grounded it to the plate. And so it's a 3,000 volt clearing field, but at like 1 milliamp. So, if you actually even were to connect it with your fingers, you would zap you like those tennis rackets zap mosquitoes. So it's a very, very low voltage, low amperage, but high voltage.
I bought a couple of broken neon signs just to get the transformer.
Right.
I mean, the Jacob's ladder
Oh, yeah.
put out at
Those are awesome.
Halloween time.
Charge
A
it.
lot simpler thing to do than this.
Yeah, this took a little trial and error, and as you can see, it's still going through plenty of error.
Is this a glass plate you have on?
No, it's plexiglass. Yeah, acrylic.
I would recommend a glass plate.
Can you see it now?
Scratch free.
I don't. I'm not actually. Let me run the clearing field. Is anything appearing now?
Not that I can discern.
Okay. Yeah, it's still like dim on this. Come
If I
in.
step away, maybe it will.
Right, it'll start working again.
So
see, I'll see if I
they
can
say
get it
that some
working
people
here.
are
See if I can get it working.
electromagnetically charged.
While everyone is.
All my forks are strange.
Hey. So welcome to the club, I guess. Like.
In lieu of having a clearing field, if I just open it up, close it again.
Let's see it with what you got, Alice. Yeah, I just wanna try to get another couple seconds without.
Right.
being able to-
Yeah, I don't know why I'm not able to, this clearing field is not working. Whew. Lordy, I get hot easily. Oh, wait. Okay, they're back. At least temporarily, so grab the video while you can, just get back.
Great quick.
Yeah. Yeah.
Yeah, you gotta get it it's focusing on the plate.
Yeah.
Put it right up against the plate here. So that it.
I don't wanna look at myself. Oh, come on, turn
Yeah, it's,
around.
yeah, that's there you go. Over there.
Okay. Here,
Yeah, there's no, can't tell if it's there or not. They're faint. Yeah, they're faint. Dadgummit.
I don't know if I took a picture either. I think I didn't.
Yeah, they are there.
Well, I think I did too. I think I had the video on.
The clearing field is not working. That's definitely the problem. Because I can see they're starting. They start, and that's why they appear and then they suddenly go away. Is because it's building up that ion cloud, like I said, and the clearing field isn't clearing it out like it's supposed to be. Unfortunately. What's that? Picocurie. A picometer. You're talking about like the wavelength of the. Oh, okay. I can see Curie's would be in it because Marie Curie would be named after her.
Definition is 1 trillion. Charitable page 3.7 by 10 to the negative. Separation per second.
Seeing the sun?
Usually used in measuring radius.
I'm starting to wonder if you're like an ion creator or something, because every time you come up here, let me see if I
Or
can.
I'm so charged up that
Exactly.
I'm the clearing field.
Yeah, see, I see them, but they are very faint.
Yeah, I'll get close to it.
Okay, there you go, that's a little better. Especially over on this side, I saw them.
I'm gonna do the presentation to warm me up quick.
Oh,
See them?
I think so.
Yeah, the white
Yes,
one,
yes.
and yeah, they're.
Yeah, I'm definitely seeing them now.
Yeah.
Yes.
Yeah, like I said, the clearing field, the charger is getting a little bit charged, so I can get a little bit of.
There are quite a few.
Oh yeah, there's
Now that I
tons.
note the movement, you know, the way that they fade in and
Right.
come, It's
Yeah.
very different than all of the previous, but.
You want me to send you a copy?
Oh, okay.
Yes.
Yeah, it's kind of like looking for four-leaf clovers. Once you see the first one, then you see a bunch of
Yes.
them.
Yes.
You gotta see that first one. So, yeah, unfortunately, my clearing field is not working as well as it should be. Oh yeah, that's the piece that I cut off. Yeah. But yeah, it is actually working now at least. So yeah, they're definitely there.
It has worked for several people,
Oh yeah,
and now I just, I'm on that list.
it just doesn't like you. Yeah, they're definitely there now. So yeah, that's the cloud chamber.
Awesome. That's awesome.
That's the gumite, which is actually a combination of like curite and uranophane. So
Yeah,
yeah.
thank you so
Absolutely.
much. That's great. Yay!
Good name, you looking for out
What's that?
Good name, like Frankenstein.
Yeah, I need to. Well, I was gonna like bring it to the show and whatnot, but I need to put like a cage around it, make it look nicer. This is kind of like the utilitarian version. It still has all of the wires hanging out and everything. So I need to clean it up, but it's at least in its functional state now.
And it's a little bit too able to be fiddled with.
Right.
Public.
Exactly, yeah. Before I would
Yeah.
ever let anybody come close to it, then when I wasn't like right here, I would want to completely enclose this entire thing. I mean, there's really nothing on here that could hurt somebody badly. You know, there's something that could maybe give them a little bit of a shock. But I mean, it has a breaker on it, and this has a breaker, and it has its own dedicated breaker on the only high voltage, high amperage device. So it couldn't actually do any damage to somebody, but it could damage the equipment, and you know, I don't want to even shock somebody a little bit. So
Right.
yeah, I definitely need to enclose it before it's ready for public viewing. But I figured for just the club being able to come up and be here next to it, nobody's wandering around the back and whatnot. So it makes it.
Take your rock.
What's that?
Knock it open, take your rock.
Exactly, exactly. Yeah, so like right now, there's almost none in there because the clearing field. Yeah, I really need to charge this thing up. But at least everybody got to see it
Yeah.
before it.
Yeah, thank you so much,
Yeah.
Charles. We'll let it run for a few more minutes while if anybody else wants to see again. And I see that some other people have brought their collections and arts to share. We'll conclude the meeting, and please we can show and tell and ask questions and or anything that you got. This concludes the meeting. Thank you everybody for coming. Thank you, Charles. And see y'all next time. Oh, sorry. So real quick though, housekeeping though. Like Dave said, we do have a field trip, and that is May 16th. That is this coming up Saturday.
Get the,
I did not get the blast out. I did get the event on Facebook for it, and I am sending out again the newsletter with the update of our presentation today. And our next Cabochon class will be in that also. We did have a Cabochon class about 2 weeks ago, and we had eight to nine people. It was a lot of people there. I think what we're going to do this time is actually stagger the arrival times for it. That way we can address situations as they come up. We had some things happen, but most everybody left with a Cabochon polished cab, and if they didn't, we did make arrangements for them to come back. But I think that staggered time, so it's time up for a time slot, like every other hour, but it'll be on a Sunday. We have figured that is going to be the best time to come and time to have them. But yeah, so I'll get that dates to y'all in this next coming letter about also the field trip and what had gone on for this meeting. So thank y'all guys for coming. Yeah.